Hopefully I'm scared. Whatever we do in class here today will be on Screencastify, so everybody's on Screencastify. You guys are famous now. You're all on TV. We'll be on Screencastify, and we'll capture everything that we do here in class today. All right, some preliminary stuff with respect to forces. Some preliminary stuff with respect to forces. These are things that we've talked about a little bit. Weight, once again, the weight is your measure of your gravitational force, measure of the gravitational force exerted on an object. Its value can be changed. Its value can change with the location of the object in the universe. If you want to lose weight on the scale, if you on Earth weigh 200 pounds, you step on a scale in your bathroom, you weigh 200 pounds. You take that exact same scale and put it on an airplane that's flying a couple miles up in the air, 5 miles, 10 miles up in the air, and step on the scale. You will not weigh as much in that airplane. Just because the gravitational force is not going to be quite as strong as it is here on Earth. If you go out beyond the atmosphere, you have the idea of weightlessness. You step on the scale on the space shuttle with no gravity turned on at that point that's orbiting the universe, you will not have any weight. Why? Because you're weightless in space. We talked about force. Force is equal to mass times acceleration, and we're talking about the weight. Our acceleration is gravity. So we deal with this acceleration. It is the acceleration of gravity. And the units, and once again, are in kilograms meters per second squared, which are Sir Fig of Isaac Newton's. It's getting close to lunchtime. I could go for a Fig Newton at this time. If a block has a mass of 10 kilograms, what's its weight? Calculate its weight. Lucas, what's the weight of the object?
98.1.
And what's the units?
Kilograms.
98.1 what?
Kilograms?
Nah, that's its mass.
Newtons.
Newtons, yeah, figs. You have 98.1 newtons, and if you want to deal with this in a negative sense, to say it's going downwards, I mean, that would be fine also. Just the idea of 98.1 newtons, that would be an object's weight, is fine. We talked about a normal force. It's the force in opposition to the force of gravity to create equilibrium. It's the force opposite in opposition of the force of gravity to create equilibrium. This is your normal force. And we dealt with this a little bit when we were dealing with an inclined plane. This was also the perpendicular force. So we've dealt with this a little bit. It's your normal force. It's a force opposition of the force of gravity to create equilibrium. And when we talk about this equilibrium, the net force on the object will equal 0. The net force on the object will equal 0. The object is just standing still. You lying in bed this morning trying to get your carcass out of bed, you're just laying there. You're not moving either way. Your inertia is very high. You're resisting motion. But you also look at the idea of equilibrium. You're not falling through the bed. You're not being sprung out of the bed. You're just laying there in the bed. So the net force on you is 0. And the bed is applying a perpendicular or a normal force on you. It's equal but opposite to your weight. It's a force from the surface back onto the object. The force from the surface back onto the object. That is your normal force. The force from the surface back onto the object. It's that bed pushing up back up on you. All right, I'm going to try something here. Hopefully this will work. I'm experimenting. Everybody's still there. Can you guys see me? Can you see me? Give me a thumbs up. All right, that's fine. We have this block. Like I said, I'm trying here today. We have this block. It's sitting on this surface. Okay, it is not being sprung back upwards. It's not falling through the surface of this block or this piece of wood here. So my normal force, my weight of this object, is pushing down onto the surface. Just like when we're standing on a surface, the surface is creating a normal force back upon us, so we don't fall through. That force is equal but opposite. Okay? If it was greater, if the force of this wood was greater than the force of weight, what would happen is the object would bounce upwards. But since this force pushing upwards is not greater than the force of weight, this object is just staying stationary. It's not falling through. It's not being pushed upwards. So this is our weight is going downwards. Our weight is going downwards in this object. The force normal is pushing upwards. It's the force of the weight or the force of the surface pushing back up onto the object. So that is your normal force. So if we take a look here, here's our 10 kilogram mass. We have weight, which is being pushing it downwards at 10 times 9.81, which is 98.1 newtons, and that's going downwards. We have a force normal, which is equal but opposite to that, which is going to be 10 times 9.81, which is 98.1 newtons. And that is a positive since it's going upwards. So that is our surface supporting our object and supplying a force back up to our object so the object doesn't fall through. When you walk, you're out there at Lake Harmony, you try to walk on the water right now out of Lake Harmony, you're going to fall through and you're going to go down to the bottom of the lake. If you get a very thin layer of ice, which will be shortly happening out there on Lake Harmony, a thin layer of ice. If you walk out on that lake, you may be able to get a couple steps on that thin layer of ice. But eventually what would happen is you would go through the ice. For those first steps, the force normal, the surface of the ice or that ice is going to push up on you and supply equilibrium. Eventually, as you walk out onto the lake, you're going to fall through, so your weight is going to be greater than the force normal. If you go out there in the middle of January and you got 8 inches or 10 inches of ice out there at Lake Harmony, you'll be able to walk all the way out to the island. Okay, if you walk out to the island, the ice is going to supply the normal force back upon you, and you will not fall through the ice. So it will support your weight. So that's the idea of a force normal. Your force normal is equal but opposite to your weight. We need something underneath us to be able to support our weight. And once again, if I take a look at my force normal plus my weight, I add them up, they equal 0. I have a 98.1 newtons here. I have a negative 98.1 newtons here. We add them up, they get to a value of 0. We have equilibrium. When you have that equilibrium, the sum of the forces on that object is equal to a value of 0. Friction. Everything we've done up till now, we have neglected friction. We were on frictionless surfaces. We did not worry about the idea of friction. But everything in the world has friction. What is friction? One of the definitions we have is a force that resists movement. A force that resists movement. A lot of it depends on the surface in contact with each other. The surface contact with each other. Every fall, and we've talked about this, I appreciate all the help and assistance everybody offered for me hauling my leaves back to the back of my woods. Thanks. But some of you also have to deal with the same thing. If I'm taking my leaves and hauling them back to the back of my woods, it depends on what the surface is that I'm trying to drag them across. If it is the pavement of my driveway, it's a little bit rougher. It's going to take more force for me to be able to drag them across my driveway. Where if I'm on wet grass, the leaves will slide a lot easier. They may weigh a little bit more, but they will slide a little bit easier. If it is dry surfaces, they won't quite slide as good as they would on a wet surface. So it depends on the surface that you're walking on. We experience this as we probably experienced it last Tuesday, when we started to have surfaces that used to be just pavement out there, and we can walk and drive on those surfaces that are dry and paved with our tires or our feet and our tennis shoes, and it was always easy to walk. But last Tuesday, when we got 6 inches of snow or 8 inches of snow, and the roads became a little bit icier, that friction between your tires and your car tended to be a little bit less. Where if I slammed on the brakes and it was dry pavement, I would stop. I slammed on my brakes last Tuesday and I had icy, slippery pavement, I would slide. The resistance to movement is that idea of friction. And when we're on wet surfaces and when we're on snowy surfaces, the resistance to movement is not as great as if I have a dry surface. Friction is what stops our car. Our brakes are the ones that stops the wheels on our car. The brakes stop the wheels from moving on our car. The friction between the car, tires, and the road is what makes the car stop. So if we take a look, we have our car here. If we hit the brakes here, it stops the tires from moving. That's all the brakes do. It stops the tires from moving. The contact between the surface and the tires is what makes the car stop moving. If this surface is wet or if it's snowy, the friction is going to be less and the car won't stop quite as fast. If it is dry pavement out there and you hit the brakes, your car will stop. Why? Because your wheels have stopped turning around and going around in circles. That's what stops your car. It's the friction between the tires and the road. If you have brand new tires and it's wet out, you'll stop a little bit quicker. If you have old tires that have 60, 70, 80,000 miles on it and there's very little tread on them and you try to stop, you'll tend to slide a little bit more. Why? Because the surface of your tires is going to be less resistance to the friction. Friction resists movement. As you walk and you take a step on ice, we start making baby steps because we don't want to take big strides on ice. Because if we take big strides on ice, we are depending on our shoes and the surface that we are walking on. And if it's on ice and I don't have much traction in our shoes or in my shoes, I'm going to slip and fall. Static friction. When you talk about static friction, it's a force that resists an object to start moving that is in contact with another surface. The force that resists an object to start moving that is in contact with another surface. So we talk about static friction. You have an object that is stationary, and it's resisting the starting of any type of movement. This is called static friction. The resistance to the start of movement. It's the force required to break the inertial force of an object at rest. The force required to break the inertial force of an object at rest. Now remember your idea of inertia. Newton's first law is the idea of inertia. An object will remain in the same state of motion or rest unless acted upon by an unbalanced force. Well, we're just looking at the idea of an object at rest. It's a force required to break the inertial force of an object that is at rest. This is your static friction. And we have a second one, which is called kinetic friction. It's one that we're more used to dealing with. And your kinetic friction is a force that opposes movement of an object that is in motion, that is in contact with another surface. So the kinetic friction is what we more deal with. That's everyday life. It's your car tires on the surface of the road. It's your shoes on the surface of the ground. You take big strides on ice, you take big strides on mud. As you're walking, you're going to tend to fall. You drive on mud. You drive on wet surfaces, you drive on snow or on ice, and you try to stop quickly. It's not going to happen. But your object is already in motion at that point. So kinetic friction is the force that opposes the movement of your object that is in motion. And if you think about just walking, you put, like the Winter Warlock, you put one foot right in front of the other. You put one foot in front of the other. I'm sorry, I've been watching too many Christmas movies. You put one foot in front of the other. What stops your foot from sliding and continuing to slide? Well, it's the traction that you have between your shoe and the surface. That's your kinetic friction. Okay, the kinetic friction. You have to have kinetic friction to be able to walk. The idea of the frictionless world would be great to live in. You never stop. You would just keep sliding until you run into something. So you have static friction, which is a force that is the force required to break an object that is at rest. And the kinetic friction is a force that opposes the movement of an object that's in motion, that's in contact with another surface. Sometimes this is called sliding friction. Friction is the opposite direction of motion. Friction is in the opposite direction of motion. So your friction will always go opposite to the motion. And once again, this is sometimes called sliding friction. Whatever your motion is, whatever your direction of motion is, you go opposite that to your force of friction. If we look at our lab table again, wake up everybody. What we have here is a nice smooth piece of wood here. Nice smooth piece of wood. Put a block on here, and I have a scale that's attached to this. The scale is basically for weight, but it also can measure a force. Because I have 200 grams here, I can also multiply this by 9.81, 0.2 times 9.81 to find what is my force of gravity. So I can utilize this to be able to apply a force also. If we take a look, this object is initially at rest. To be able to break my motion, okay, or to be able to break this right here, that it's at rest, I have a force. I'm applying a force right now, but the object still is not moving. So I have not applied enough force yet to break what is called the static friction. The static friction is the friction required to get the object moving. Okay, so as I'm pushing or continue to pull, you can see the dial here continues to increase. So as I continue to pull, what you can see with this dial is as soon as the object starts moving, if you look at when this object starts moving and watch the dial here, what will happen is this dial will start going backwards. Where here, and then it goes back to here when the object starts moving. So as I start to pull this, it doesn't take as much force to keep the object moving. Okay, so the force is going to be less to keep the object moving, which means the static friction is going to be greater. If I take a look at a little rougher piece of wood, and I do the exact same thing, since the wood is a little bit rougher, it should take more force to get the object moving. But once again, once I get the object moving, the dial will go backwards because it's my force to get it moving is right there, and then to keep it moving, it's not as much force to keep it moving. So my force required to start something is not as great as the force required to keep it moving, which means my resistance to get things moving is higher than the resistance to keep it moving. Okay, the force required to start something moving is greater than the force required to just keep it moving. Well, the force required to keep it moving is counterbalancing sliding friction. The force required to start things moving is counterbalancing your static friction. It's easier to keep an object moving at a constant speed than it is to start the object moving. It is easier to keep an object moving at a constant speed than it is to start an object moving. And that was what I was trying to demonstrate with that dial, as it took me more force. I had to pull harder to get it moving, but once I got it moving, I didn't have to require as much force to get it moving. Just as I'm trying to pull my leaves back to the back lot every fall, once I get it moving, the easier it is to keep it moving. But initially, it's sometimes tough to get it moving. Which means your static friction is going to be greater than your sliding friction, or your kinetic friction. It's easier to keep an object moving at a constant speed than it is to start the object moving. There's no difference than in the morning as you're getting up out of bed. Sometimes it's tough getting up out of bed in the morning, but once the old adage, once I'm up, I'm okay. I'm moving around, I'm okay. Your personal static friction is greater than your personal sliding friction. Once it's tough getting out of bed in the morning, but once I get things moving in the morning, it's easier. But it's tough getting things moving. So if I would take a look at what was happening with my initial demonstration over here, I continued to apply a force, okay? And during this time, we were stationary with our object. We were stationary with the object. Until we got to this point right here. At this point, we broke static friction. We broke static friction, and we had movement. It moved. The block moved. So that is this point right here. We apply a force, the object is stationary still, till we get to this point right here, and all of a sudden we broke static friction, and we started getting movement. And then at this point, we start moving at a constant velocity. It will drop in the amount of force that we have, and then we'll start moving at that constant velocity. And that's what that little dial, the little meter, or the spring scale that I used, showed that it took more force, because I can multiply that by 9.81 to get a force, and then to get it starting to move, and then when I get it moving, the dial or the little arrows went back some. So we're stationary, At this point, we break static friction, and we start moving at a constant velocity, and then we have just kinetic or sliding friction. We have to have enough force to counterbalance static friction. So our force applied will equal our force of friction. These will be equal but opposite. They'll be going in opposite directions. Because if we go back up here with the constant velocity, if we have a constant velocity, here we go, here's a question for you. If we have a constant velocity, the velocity is a constant. What is the acceleration of the object? If our velocity is constant, what is our acceleration of the object? Jordan?
0.
0. So if my acceleration then is going to equal 0, my force net is equal to mass times acceleration from Newton's second law. From Newton's second law, force net is equal to mass times acceleration. Well, we're saying our acceleration is equal to 0. So if I have a constant velocity, my acceleration is equal to 0. My force net is equal to 0. If my net force is equal to 0, we then have equilibrium. If we have equilibrium, we have balanced forces. Which means our inertia properties will hold true. Newton's first law. Newton's first law. Objects will stay in the same state of motion or rest unless acted upon by unbalanced forces. We have balanced forces, so we're going to stay in the same state of rest or motion. If you're traveling on a flat surface, you take your foot off the gas pedal and just let the car go. Hopefully steer it so it doesn't run into the ditch. Your car will eventually stop. The reason why is there's going to be friction between the surface and the tire still. There'll be friction that's internal within your car. Your tires will have some friction. Okay, that's the reason why we grease certain things, so that we reduce the idea of friction. But friction is still going to be existent. If friction is still going to be existent, the object is going to slow down. Your car eventually is going to stop. It will eventually stop. Why? Because force is slowing it down and stopping it, or force of friction is slowing it down and stopping it. Because there's no other forces that are existing at that point. For you to maintain a constant velocity, so you have to keep your foot on the gas pedal. The coefficient of friction. Oopsie. That was the link to your calc notes. The coefficient of friction is the magnitude, the ratio of the magnitude of the force of friction between two surfaces in contact to the magnitude of the normal force. The ratio of the magnitude of the force of friction between two surfaces in contact to the magnitude of the normal force. This is your coefficient of friction. The ratio of the magnitude of a force of friction between two surfaces in contact to the magnitude of a normal force. It's dependent on the surfaces. It is dependent on the surfaces. The ratio of the magnitude of the force of friction between two surfaces in contact to the magnitude of the normal force. Depending on the surfaces. Wake up, Liam. We have this nice smooth board here. Nice smooth board. It doesn't take much to get this object moving because it's on a nice smooth surface. I take this rough piece of wood, the exact same surface of the block, same weight. It's going to require more of a force to keep the object moving at that point. Why? Because we have a rough surface. If I take a look at just this tabletop here, which is even smoother than the table, or that first piece of wood, as I thought it was, it's very similar to the first piece of wood. If we would get lemon pledge out, get the lemon pledge out and put it on the surface here, make it nice and slippery, okay? We can slide it right across. If we were on a slippery ice, we can slide it across. Think about if your parent, or if somebody gets the lemon pledge out and waxes some woodwork around your house, okay, and some of it gets on some hardwood floor that's close to, or that you're walking on, and you're in your socks, and you step on that lemon pledge that's on the floor, you slip and go flying. Okay, that's the same. You change the surfaces by putting the lemon pledge on there, and it makes it a lot slipperier. Slipperier, if that could be a word. So mu, okay, the symbol that we use for our coefficient of friction is mu. It's defined to us as the force of friction divided by our normal force. Mu, and that's the same mu that we use in statistics. It's a U with a tail. Mu is our force of friction divided by force normal. Which, if I multiply both sides by my normal force, my force of friction can be calculated by mu times force normal. The force of friction can be calculated by mu times force normal. We want to calculate the net force in the acceleration of the object. It's a 10 kilogram force, or 10 kilogram mass. We have a force applied, which is 25 newtons, pulling it to the right. So we are pulling it that way. And we have our coefficient of friction, mu, is equal to 0.15. We want to find what the net force is. Well, the net force is the sum of the forces in a direction. So we are just dealing with horizontal forces in this case, because we have a horizontal plane as we go along here. If the object is being pulled to the right, the object has motion going in this direction here. Our force of friction, if my motion is to the right, my force of friction will be in which direction? Dylan, what will be our force of friction? Which direction will the force of friction go?
To the left.
To the left. So we're going to have a force of friction, whoopsie, a force of friction that's going to push it towards the left. It's going to resist motion. Okay, it will resist our motion. Well, how do we calculate our force of friction? Our force of friction is mu times force normal. Well, how do we calculate our normal force? Katie, how do we calculate a normal force? How do we calculate our normal force?
Would it be the mass times acceleration?
That's exactly correct, because we have a weight that is our force of gravity going downwards. Our force normal is the force that's pushing back up from the surface. So our weight is pulling it downwards. Our force normal is pushing it upwards. Once again, this object is in equilibrium. Okay, in a vertical sense, up and down is an equilibrium because it's not jumping off the table or it's not breaking through the surface. So we have to have equal but opposite forces in the vertical sense. So my weight is what's being pulling it downwards. My force normal is going equal but opposite to that. So our weight is equal to 10 times 9.81, 98.1 newtons, which is going downwards. My force normal is equal to opposite to that. So my force normal is going to be 98.1 newtons. That's going upwards. Our force of friction is calculated by mu times force normal. So we have 0.15 times 98.1 newtons. So Nate, what is our force of friction?
14.72 newtons.
And that's going to the left, so that will be a negative motion. I have 25 newtons going to the right. I have force of friction that's resisting your motion going to the left. So looking at our force net is the sum of the forces, and this is just horizontal. So we have 25 newtons plus a negative 14.72 newtons. So Andrew, what is our net force going to be? We have 25 newtons going to the right. We have negative 14.72 newtons going to the left. Our net force would be what? Andrew? Andrew?
Sorry, my mic wasn't turning off. Would it be 10.2?
10.28. And that's going to the right, so that is our net force. So if that is our net force, our force net is equal to mass times acceleration. So our force net is 10.28 newtons. Our mass is 10 kilograms times our acceleration. We can divide both sides by 10 by 10. So our acceleration of the object is 1.028 meters per second squared. So key ideas here. Key ideas. Okay, how do we find this normal force? Okay, is your perpendicular force, it is opposite to weight. So if weight is going downwards, my force normal is the surface pushing upwards. Once again, as you walk, you're not springing upwards because the floor is pushing you upwards on every step. Okay, most normal floors are not like that. I know you can get some sort of fun floors that you get on that will spring upwards. So our force net, or force normal, is equal but opposite to weight. We have equilibrium there. The force of friction resists movement. So when you're talking about friction, you're resisting the idea of movement. Depends on the surfaces. You have static friction that resists the start of movement. You start moving, that's your static friction. Your kinetic friction is for objects that are in motion already, sometimes called the sliding friction. But the static friction is going to be greater than the sliding friction because it's harder to get things moving than it is to keep them moving. Coefficient of friction is your force of friction divided by your force normal, or what we will utilize quite a bit is your force of friction is equal to mu times force normal. And whatever your motion is, wherever your direction that the object is moving, force of friction will go in the opposite direction. Okay, your car tires, as I said, you take your foot off the gas pedal. Okay, your car tires will want to continue to spin, but they will start slowing down as they spin because you have friction. You have friction in the wheel bearings, you have friction in just the mechanics of the car, but then you also have friction that is between your tires and the road surface. So those are all frictions that are going to slow the car down. And when you're talking about your force net, is the sum of the forces in a direction. Okay, in this case we just had horizontal Tomorrow what we'll do is we'll come in, we'll start dealing with an inclined plane. We'll start working with the inclined plane and looking at the force of friction in regards to the inclined plane and what's going to occur at that point with our force of friction and sliding down the inclined plane. Questions? All right, QED, I'm about done with my time. We'll start into the next set of notes tomorrow, or I'm sorry, on Wednesday. And we'll get into some more problems also. I will start posting some problems for you to be able to also do at that point. Questions at all? Once again, I will post everything here. Everything is captured and I will post it so you'll have access to any of the notes that you need. Other than that, unless you have any questions, adios. I'm out of here. Folks, have a good rest of the day. See ya.
Thank you.
Yep.
Hey, Mr. Gregory.
Yeah.
You said something at the beginning of class about a packet that you gave to the students.
Yeah.
Since I wasn't there, since I was quarantined, is there any way you can like send me the packet online?
What I
So
can,
print them out?
yeah, or you can even, do you have a printer or access to your printer?
Yeah.
Okay, that's fine. I'll just email you everything I gave everybody.
Okay, thank you.
Yep, not a problem. Any other questions?